Question 3 is a bit of a weird question on difference equations. You can read all this by yourself, and I'd recommend you do, but the important stuff is just the equations they give us. So this is the difference equation we're given to base everything off. So this is the difference equation, and then we're told things about Pn. So Pn, we're relating Pn with Gn, and we're told what A is here as well. This stuff doesn't matter, it's just about what n is, what n can be as a number. Then we're told what In is in terms of Pn, and then obviously we know Pn in terms of Gn. And basically, we're told to use this information to get a second order inhomogeneous difference equation for G and express it in this form. So with all the G terms on the left and S on the right, and we're asked to find the coefficients of Gn plus 1 and Gn, which they've called C and D. We're told to calculate C and D. So this is a bit of a weird question, but we'll plow on through it. So basically, we're told to figure out the last thing. So we're going to take what we know already. And this is the basic difference equation we know, this first underlined red. We know that Gn is going to be equal to Pn plus In plus S. Now we see in the form that we have it, we have S on the right side, and we have all the terms kind of on the left side. So let's take the Pn and the In to the other side. We'll get the Gn minus Pn minus In equals S. Now we just need to replace Pn and In. We need to get those in terms of Gn, which we can do. So let's take the second equation. So let's look at equation 2. We're told that Pn plus 1 equals A times Gn. And A is 15 over 6. So you can actually write 15 over 16 Gn. It's 15 over 16, not 15 over 6. Now, since in our original equation that we're working with up here, we have a Pn, but here we have a Pn plus 1, it's actually an easy fix. So if we're saying that the Pn plus 1th term is given by the Gnth term, it means the exact same thing. Say that the Pnth term is given by 15 over 16 Gn minus 1. So all I did is I took 1 away from these n terms, but it's still saying the same thing. It's saying that the next P term is given by the previous G term. This is also saying that the next P term is given by the previous G term. They're the same thing. So that's our Pn, and we can put that into our original equation, but we won't do it yet. We'll do it at the end. But basically we know this now, so that's good. And now we need to find out In. So we know that In plus 1, n plus 1, is going to be equal to B, and B is 3/5, as we're told here. 3/5 of, and then we have Pn plus 1 minus Pn. Well, we have both of those. This is Pn plus 1 here, so we can replace the Pn plus 1 there with 15 over 16 Gn. So we'll have 15 over 16 Gn. And then we'll have minus Pn, and Pn is this one here that is boxed in white. So we'll have 15 over 16 Gn minus 1. So let's just do some simplification. We can take out 15 over 16. So we'll have In plus 1 will be 3 over 5 times 15 over 16 times Gn minus 1. And then we can just simplify that a little bit further. And we can say that and I'm going to actually do two things here. So we know In plus 1, but in our equation up here, we just have an In. So I'm going to do the same thing that I did with the P. I'm just going to, instead of saying that the In plus 1th term and Gn minus 1, I'm just going to move all of these n's one term down. So it's still conveying the same information. It's just one term down. So we'll have, if we can say that In equals, and then when you multiply these fractions together, you get 9 over 16. And then we'll have Gn minus 1 minus Gn minus 2. So it's still telling us the same information. The n plus 1th term depends on the nth term and the n minus 1s, except now we have n minus 1, and n minus 2. It's just we're rewriting it differently, but it's conveying the same information. Now we can sub our values, so that's going to be our In. Now we can sub these values back into our original equation, which is this. So I'll copy this down. So finally, we will have that Gn minus Pn, which is 15 over 16 Gn minus 1. So we'll have 15 over 16 Gn minus 1 minus, and then we're going to have the In, which is this big thing. So we'll have 9 over 16. And I'm actually going to expand it out because we'll see that we have a Gn minus 1 here and a Gn minus 1 here. We will have to combine those. So I'm just going to expand this out. So 9 over 16 times the Gn minus 1 will give us just 9 over 16 times Gn minus 1. Then the 9 over 16 times the Gn minus 2. Now we have a minus here, and we have the minus here. So we're going to get plus 9 over 16 Gn minus 2. That's equal to s. Then we just have to combine like terms. We can combine these two together, and we'll get the gn minus, when you add these together, you get 3 over 2. We have gn minus 1 plus 9 over 16 gn minus 2 equals s. And then finally, the form that they asked for is they have gn plus 2, gn plus 1, and gn. It's the same thing here. We just have gn minus 1, gn minus 2. You can do the same trick. This saying that the n plus 2 second term is the term before that plus d times the term before that. This is the same thing. It's just scaled down. It's telling out the gn minus the term before and the term before that. So we can actually just scale this up by adding 2 to each of the ends. So we have the gn plus 2 minus 3 over 2 gn plus 1 plus 9 over 16 gn equals s. That kind of looks like a 5, but that's an s. And that's our final answer. Now we do have to do what the question asks. So it says the values for c and d. Well, c is just the number before the n plus 1. So the number before the n plus 1 is minus 3 over 2. So c equals minus 3 over 2. Notice that it is minus because in the original equation, this is a plus, but here we have a minus. So we have to make sure we're taking that minus into account. And then d is the number before the gn, which in our case is 9 over 16. 9 over 16. And that's part 1. So then we're assuming that the government spends no money. So we're assuming that s is 0, that g can be expressed by this. And then we're told that the initial G0 is 840 and G1 is 820 in billions of euros. We're told to solve the difference equation to find an expression for Gn in terms of n. And then we're also told to calculate G6 to the nearest billion euros. So we always use the same method for solving a difference equation. Second order inhomogeneous. Well, I'm using the same method for all of them, but I think everyone uses the same method for this one. So we'll have gn plus 2 plus c, and this is just what we have up here. Our c is minus 3 over 2. Minus 3 over 2 gn plus 1 plus 9 over 16 gn equals 0, and we basically just have to solve this. So I guess first of all we'll get the characteristic equation. So this is the top term, the n plus second term, this is the term before that and the term before that. So we have 3 terms. So the highest one will be our x squared or our or squared, whatever you want to call it, the root, minus 3 over 2. Since we're going down 1, we'll go down one term, we'll go down 1 power x, plus 9 over 16 will be our constant, because that's x to the power of 0, which is 1, equals 0. We can multiply it across by 16 to kind of simplify this a bit, I suppose, or you can just use the quadratic formula. I actually might just use the quadratic formula, might be easier. So we'll say that x equals negative b is 3 over 2, so we'll get 3 over 2, which is 1.5. I'll just write it as that's a bit easier. 1.5 plus or minus the square root of 1.5 squared. Well, technically it's minus 1.5 squared, but it doesn't make a difference. Minus 4 times 4a, so times 1, times 9 over 16. All over 2 times a, and a is just 1, so over 2. So x equals 1.5 plus or minus, and then this ends up being, the thing under the square root ends up being the square root of 0, which is just 0, so I'm just going to leave it out. So we actually just get 1.5 over 2, which is equal to 1.5 over 2. It's 0.75, or 3/4 is a nicer way of writing it. So we actually have a double root here. We have a root that's the same, because in a quadratic, obviously, we always have 2 roots. So we have the same root, which means that our difference equation is going to be a little different. Don't think they've actually asked difference equation with repeated roots in an exam yet, so this is interesting. So that means our solution will be in the form a times 3 over 4. Sorry, I should put that on the whole thing. We might say 0.75 for now, just to make the bit neater. 0.75 to the power of n plus bn times 0.75 to the power of n. We have to put that n there because it's a repeated root. Otherwise, we'd be able to combine these terms, and it's not actually second order then. I might make a video about that in more depth, just because I think it's not explained super well in the book. Then we just need to find a and b using these equations here. So we're told that G0 is equal to 840, which is equal to, and these n's will be 0, so we'll just have a, because that n will be 0, that this term's gone when we have plug in 0, and then 0.75 to the power of n is 1, so we get a is 840. So that's actually quite nice. So now we know that gn equals 840 times 0.75 to the power of n. plus bn times 0.75 to the power of n. Now we just need to find b. We know that g1 is 820. So we'll have g1 is 820, which is equal to 0.75. Well, actually, I'll write it the way that it's there. Just replacing all those n's with 1. 840 times 0.75 plus b times 0. Sorry, n is 1. So b times 1 times 0.75. So we'll get 820 equals, what's 0.75 times 840? Gives us 630 plus 0.75b. Bring the 630 to the other side, and we get 190 equals 0.75b. Divided by 0.75b will be 190 over 0.75, which is equal to 190 over 0.75. It's actually a decimal. Well, I'm going to write it as a fraction because it's a recurring decimal. It's 760 over 3. So finally, we can write it as gn. You probably could round it up, but I don't, when it's a recurring decimal, I like to keep it as it is. So gn will be 840 times 0.75 to the power of n plus, and now instead of bn, we'll have 760n over 3 times 0.75 to the power of n. I guess you could write it a little bit easier, just when we're doing our calculations a little bit easier. If we factor out the 0.75 to the power of n, and we multiply that by 840 plus 760n over 3. And that's the way we can write it. You can write it other ways, but I think that's the nicest way to write it. We're also asked in this part to calculate g6 to the nearest billion euros, so we're just replacing that n with a 6. So what we'll get is we'll get that g6 equals 0.75 to the power of 6 multiplied by 840 plus 760 times 6 all over 3. Put that into your calculator. And you'll get 420.029, and it says to give it to the nearest billion euros. So that's going to be 420 billion euros. So we can just use the euro sign there. 420 billion euros. In part 3, we're assuming that the government spends 40 billion euros each year, so it's no longer homogeneous because we have a 40 on the right-hand side instead of just a 0 like we had up here. And we're told to just solve it again. We have the same initial conditions, and then calculate g6 again. So we can kind of reduce some of the work because the homogeneous part, the part with the gn's, is actually going to be the exact same here as here. So we're still going to have the same complementary solution, but the coefficients will be different when we take into account that 40. So we can actually just take down this much here, and I guess we can rewrite it just to be a little bit easier as 0.75 to the power of n times a plus bn. So that's actually only our complementary solution this time. It's not the full solution. And then our complementary solution is, again, it's only just a constant like in the previous question. So our particular solution, sorry, is what I meant. It's just going to be some constant, which we already have a d, so I'm just going to call it m, because m tends to be one that they use for constants. And then we need to get this for n plus 1 and n plus 2, so that we can sub it back into our original equation. Now, since it's a constant, it actually doesn't matter. It's always just going to be that constant. So gn plus 1 and gn plus 2 are both just going to be m equals m. We just sub them back into this equation. And what we'll get, we know what c and d are, so what we'll get is m, replacing this gn plus 2 with m, because that's our particular solution for it, plus c. Now c is just minus 3 over 2, as we calculated in part 1, so we'll have minus 3m over 2, and then d is just 9 over 16, plus 9d over 16, sorry, not 9d, 9m, d is 9 over 16, and that's going to be equal to 40, and we just need to solve for m here. So you could multiply by the common denominator of 16, but I think a quicker way is we can factor out m. We'll get m 1 minus 3 over 2 plus 9 over 16 equals 40. If we just do m equals 40 and then divide it by that stuff, or we could just figure out what's in the bracket. So when we do that stuff in the bracket, we end up getting m times 1 over 16 equals 40. Multiplying both sides by 16, we get 16 times 40. M equals 16 times 40, which is 640. And that's going to be our particular solution as well, because Gn, remember, our particular solution, that was just equal to m, so our particular solution is just 640. And now our final solution is going to be the sum of our particular and complementary solution. So we get that Gn equals, we'll have 0.75 to the power of n times a plus bn plus 640. And now we just need to find out what a and b are. So we know that G0 is 840. So what we'll have is that G0 equals 0.75 to the power of 0, which is just 1. So we'll just get 1 times a plus, and then since n is 0, it'll be b times 0, which is just 0, a plus 0 plus 640. And we know that G0 is equal to 840. And this is why we have to recalculate a, because remember last time we just got a equals 840, but now we have to take this 640 into account. And when we take away 640 on both sides, we get a equals 200. Sub that back into our original equation, we get that Gn equals 0.75 to the power of n times 200 plus bn plus 640. We're told that G1 is 820. So we have G1 is equal to 820, and we replace all the n's with 1, so we get 0.75 times 200 plus b times 1, which is just b plus 640. Bring the 640 to the other side, you get 820 minus 640 is 180. So we'll have 180 equals 0.75 times 200 plus b. I might actually expand that bracket out as well. So 0.75 times 200. I just want double 0.75 just because I don't want to make stupid mistakes, even though I'm pretty sure I can do them in my head. 150 plus 0.75b. So 0.75b equals, bring the 150 to the other side, 30, and then 30 divided by 0.75 is 40. So we get that b is equal to 40. So it actually works out nicer than in part 1. Finally, Gn, or not part 1, the previous thing we did, 0.75 to the power of n times 200 plus 40n plus 640. And that's our equation for the spending of the government. I think that's what it is, or something like that, after the nth year. And again, we need to find G6 to the nearest billion euros. Don't really know why they say that. I guess maybe just so people won't be expecting. I guess they can't really give hints as to whether you got it right, so they can't. They're using just the same wording as the previous part. Sorry, we're looking at G6 here. G6 is just 0.75 to the power of 6 times 200 plus 40 times 6 plus 640, giving us an answer of... Actually, there is a reason why they say to the nearest billion euros. Is this 0.75 to the power of 6? That's not a great decimal. What we get is 718.31. It says to the nearest billion euros, so we'll have 718 billion, and we're in euros, and that's our answer. So it's also interesting just from like I suppose an economics perspective. If the government spending is higher, I think that's what it said. Yeah, the government spends 40 billion euros each year. They'll actually end up having more, whatever G is. I didn't really properly read the question either. Is actually going to be higher than what it was here, where G is the government spending. So yeah, you can see it works out. It's a very interesting way of modeling stuff with difference equations.